Okay, so the plan for our second to last class meeting is to finish up hypothesis tests. So we'll finish chapter 8, discuss a brief topic in chapter 9, testing for difference between two means, and then plus or minus, we might get to a PowerPoint on some cautions and pitfalls of hypothesis testing. It's kind of a longer PowerPoint, so we certainly won't get through all of it, but it just covers some of the challenges with interpretation and analysis of hypothesis tests. As I mentioned previously, there are supplemental videos posted for chapters 11 and 12 to make up for the day that we missed. So those are up on YouTube. And then on Monday, we have a discussion on correlation or regression. So we do have class this coming Monday. That being said, we have our final exam that is going to be open this Friday at 9 a.m. and open through Friday the 9th at 11:59 p.m. So if you wanted to take that exam early and you want to look over the correlation regression material first, you can check out one of my other stats YouTube playlists from a previous semester, like the fall 2024 playlist, and you can, pull the correlation regression lecture from that playlist and watch that. So, but it's just like 11 and 12, it's a fairly large topic that, we're not covering really in any depth at all. We're really not doing it justice. We're just going over kind of an introduction to it, just an expository lecture on it. And really the same can be even said about chapter 9, testing for difference between two means. So really everything after chapter 8 is really just meant to expose you to some different ideas that build off of some stuff that we've already worked with that you might see in future courses or in journal articles, things like that, and give you a jumping off point if you wanted to research them more. Okay, some information about final exam week. So the proper final exam week is really Tuesday, what would that be, the 6th through the following Monday, but for our remote and online classes, we end the semester on Saturday, the 10th. So our final exam week really runs from Tuesday through Friday night. But I'm opening up the final exam this Friday, so a couple days from today. So that way, if you want to make use of the weekend, you certainly can do that. But, don't feel compelled to take it early. But if you want to take the exam early, you can. It's not comprehensive. It covers chapters 7 through 12. So basically from confidence intervals and hypothesis testing, that'll be most of it. And then a few selections from the other kind of ancillary material that we are going through at the end here. No ProctorU, no Examity. We've discussed that before. The sample exam is available now. I made the sample exam and final exam and all of that. I set all of that up this morning and got everything live. So you should be able to see the sample exam now. It's at the top of the assignments page. So I put the exams at the top just so they're easier to find. They don't get buried in amongst all the homeworks. Same note as with the previous unit exams, don't wait until the last minute to take the exam. I would actually, not Thursday, I would recommend taking it on or before Wednesday night. Since we only have until Friday for the final exam week, I'd recommend planning to take it no later than Wednesday night. And then if something does go wrong, you have a 2 full day buffer to reach out to me to, get whatever tech issue sorted out, to come up with another plan, anything like that. So I recommend planning to take it on or before Wednesday night so that if something does go wrong, there's some buffer. There are no due date extensions on the exams, and especially not the final exam, given how close it is to the turnaround for getting grades posted and all of that. The exam is closed book and notes, but you may use calculator. You can use Excel and or StatCrunch, the kind of built-in Excel simulator in my stat lab. And you can use the formula sheet and tables that I posted in the supplemental materials folder. So if you go to Blackboard supplemental materials folder, under the subfolder exam materials, you should see a PDF titled Final Exam Formula Sheet / Tables. And you can open that up. You can either save that as a PDF to like your desktop and access it that way. You can access it on Blackboard online, although if it were me, I would want a local copy just in case something went wonky with Blackboard. And or you can print it out and have it, sitting next to you as a physical copy. So um, this packet includes formulas from the Unit 1 and Unit 2 exams, as well as from more recent material, as well as all of like our normal tables, our t-table, our chi-square table, those kind of things. Okay, so that's a rundown of the rest of the course. And the quote of the day today is, don't underestimate the impact of survivor bias. So particularly when you're looking to be successful and you see other people who are successful in the same way, it's really good to look at, people who have been successful at what you want to be successful and maybe take some inspiration from them a bit. But you have to realize that the people who are very successful uh, often are kind of exhibiting survivor bias. We've talked about survivor bias before in the course. Remember, that was for example, the Abraham Wald plane study, where should we put the armor on the planes while the ones that come back with a bullet hole in a certain area, presumably the plane can take a hit there and not get shot down, but it's it's the areas where we don't see the bullet holes, so we should put the armor, because the ones that took hits there were probably the ones that didn't make it back. Right. So what are a couple examples of this? Well, some people who are looking to start working out, they'll say, oh, well, Arnold Schwarzenegger, famous, bodybuilder guy, right? He must have known what he was doing. They'll grab one of Arnold's workout, plans and then try to just implement that for themselves. Well, the problem is you're not Arnold, right? You don't have the genetics, you don't have the like single-minded focus. Like this was his entire job and career for a long period of time. He built himself up to be able to do this. Um, when you're trying to balance a half a dozen other life demands and you're not getting the same sleep or recovery that he's getting, not to say nothing of pharmaceutical supplementation, um, maybe Arnold's workout program isn't the best for most people, right? Maybe 1 out of 1,000 people can tolerate it and do really well, but chances are that's going to burn you out. Or you look at maybe somebody like Robert Kiyosaki. He published a book called Rich Dad, Poor Dad. So kind of an interesting, like, basic finance book. And one of his principles, I guess you could say, or like strategies or something like that, is he was in real estate and he basically said, okay, take on as much debt as you can, get as many assets as you can with that debt, like basically buy a bunch of houses and start renting them out. And then when the collection calls start coming in because you can't meet your payments, that will drive you to innovation. That'll make you figure out a way to make those payments. And that sounds great because it worked for Kiyosaki. But then you have folks like Dave Ramsey who did something similar and went bankrupt, right? And now he's like on the other end of the extreme, like don't ever take out any debt for anything, more or less. So, okay, that worked for Kiyosaki, but maybe he's the 1 in 1,000 that actually does work for, and the other 999 people either suffer mental health, problems, or go bankrupt, or are ruined financially for 5 or 7 years after a bankruptcy. So, don't look at these people who did something extreme and were highly successful and think that you can just do exactly what they did and become them. So we'll see when we talk about correlation regression a bit, that the end result of whatever process is typically dependent on systematic effects that are uncontrollable. So maybe things like your genetics, systematic effects that are controllable, things like, do you go to the gym and actually work out? Like that's something that's systematic. If you do it, you're going to do better, and also something under your control, and also a bit of chance or luck, right? Like, are you able to just go to the gym and you happen to not get injured as often as other people? And large outliers, this is kind of a Charlie Munger idea. Large outliers are likely a confluence of many tendencies. So you'll see somebody like Arnold or somebody like Kiyosaki or any of these people who were the people writing books about how to do what they did. yeah, they're telling you how to manage this, the controllable systematic effects, but they also likely had pretty good uncontrollable systematic effects and also pretty good luck, frankly. Just pretty good fortune, that Kiyosaki didn't do his crazy strategy right as the housing market was busting or something like that. Okay, so don't underestimate the impact of survivor bias. Thought for today. All right, so jumping down to chapter 8, continuing on with our t-test for mu. Remember last time we discussed the z-test for mu when we were estimating the mean by x bar observed, but we supposed that we knew the population standard deviation. That was the z-test for mu, kind of paralleled the z-interval for mu from confidence intervals. And the t-test for mu kind of parallels the t-interval for mu from confidence intervals. This is where we are estimating, let me shrink this just a tad. This is where we are estimating the population mean by x bar observed, and also the population standard deviation we're estimating by the sample standard deviation, S. So this is when we use a t-test. When we use the t-distribution, we're estimating two things, so we need to have a little bit more, a little higher variation. Okay. I actually think I want to change this. There we go. Okay, that looks good now. So let's take a look at this example. So example 2 from the t-test from you, we did example 1 last time about the city that wants to say their average commute times are less than the national average. So on to example 2. A college believes that their students sleep on average at least 7 hours per night. The college takes a sample of 10 students and finds a mean sleep time of 6.64 hours and a sample standard deviation of sleep times of 1.08 hours. We assume that sleep times are normally distributed, and the question is, at the 1% level of significance, can the college make the claim? And so again, maybe we want to make the statement in our marketing materials, or maybe there's some accrediting body or something that says like, or maybe student health or something like that is part of what that body is interested in, and we're trying to make this claim and we want to substantiate it. So if we look at this statement here, we're trying to argue that our students sleep at least 7 hours per night on average. So if we set up our hypotheses, we're making a hypothesis about mu. So mu would be our true mean, the true mean sleep time for our students. We're trying to make the argument that mu is bigger than 7. So that'll be our alternative hypothesis. And our null will be mu equals 7. And that really encapsulates kind of all of the mu's less than or equal to 7. Now, if I have x bar observed of 6.64 hours, do I think this is in any way evidence against the null and in favor of the alternative? Well, no, I wouldn't think so, because it's not even on the right side of things, right? This is a right tail test. X bar observes that are quite large. If I sampled my students and got an X bar observed of like 9 hours of sleep per night, then that would be really strong evidence against H naught and in favor of H1. But here I'm not even on the correct side of things, right? So maybe I look at H naught and I say the chance of getting an X bar observed that looks like 6.64, if the true mean was 7, maybe that's very unlikely. But note that it will be even more unlikely if the alternative was true, if the mean was bigger than 7, because then 6.64 would be even further away. So remember, we don't only need our X bar observed to be unlikely under the null, it also needs to be more likely under the alternative. So we'll edit this and we will make this 7.64. I put that 6 in there just to kind of make that point. Just wanted to to note that. But if we had X bar observed as 7.64, well, now my X bar observed is bigger than 7. But my question is, well, I know there's a bit of sampling error. I took a sample of size 10. Maybe I just happened to grab a few extra students who got a little more sleep last night. Maybe um, maybe I was not, standing outside the coffee shop, but standing outside the library or something, and got a few extra students who got a little more sleep than is typical. And my X bar observed is just a little bit high because of sampling error. How do I know that that's not the case? Well, my question is, not only is X bar observed bigger than 7, but is it in essence so much bigger than 7 that it becomes impractical to just explain it away by saying, oh, that's just sampling error, right? If I were to dig in my heels and insist that the null is true and that the mean is actually 7, is this so far away? Is there so many standard errors above 7 that it would be silly for me to keep insisting that the null is true, but I really ought to reject the null in favor of the alternative and presume that there's a systematic increase in mu. So that's my question. My sample X bar observed 7.64. My N is 10. We're assuming normality, so we don't have to worry about the small sample size. And our sample standard deviation of sleep times S 1.08 hours. Now, last time we we got a rejection region, and we saw that was kind of the natural approach for using a t-table to get a rejection region, because we're given t indices that we can find rather than being able to find probabilities, right? In the normal table, we can find probabilities very nicely and get p-values, but that's a little harder to do or a little less practical to do in a t-table. Let's actually take a look, though. Let's try to use the p-value method. But here we're going to have to kind of back our way into a p-value. We're going to try to estimate the p-value for this sample. So let's start off by assuming H naught is true. Remember, what we're always looking at most directly is the type 1 error. We're going to say if we reject the null on the basis of this sample, but the null was actually true, that's when we make a type 1 error. What would that rate be if we rejected for this sample? And how does that compare to alpha, or a level of significance, the maximum allowable type 1 error rate? If we make an error in practice that's at a lower rate, that's lower likelihood than the maximum allowable, then we reject. If it would be a higher error rate than is allowable, then we don't reject. Okay, so I have I'm going to kind of put it in quotes, a t distribution, kind of. If the null is true, this is going to be centered at a mean of 7. And I might be interested in finding, I see that this is a right tail test. And it's a one tail test. So I might be interested in finding an upper bound here that can serve as a cutoff. And then I say, well, if X bar observed is bigger than U, we reject H naught, or if X bar observed is less than or equal to U, do not reject H naught. Okay, so this is kind of a t distribution, but I know that t distributions are always standardized, right? All of these distributions over here are kind of like standard t distributions. So let me actually take a look at t observed. This is going to be X bar observed minus the null hypothesized value of mu over the standard error S over root n. Or it's going to be 7.64 minus 7 over, and that S is 1.08 over root 10. And if I bring up my calculator, what do I have? That 1.08 over root 10 in the bottom flips the root 10 up top. So I have a root 10 on top times the difference between 7.64 and 7. Well, that's just 0.64. And then over 1.08. Or that's about 1.87. So I could rephrase things in terms of the critical value. I might have some t critical. And then I see that this is a right tail test. So then I can say if t observed is bigger than t critical, reject h naught. Or if t observed is less than or equal to t critical, do not reject. Right, so we get a very analogous situation to our rejection region method, but in the kind of standardized world. Now I know what t observed is. It's about 1.87. And I know that for some t criticals, like maybe 1.7 or 1.6, I can reject. And for other t criticals, like 2.5, I could not reject. So my question is kind of, well, for what t criticals can I reject and for which ones can I not reject? And what are the associated p-values for those? What are basically the alphas? What are the significance levels where I can reject versus not reject? That'll help me narrow down what my p-value could possibly be. I need one more piece of information. To know anything about my t criticals, I need to know which t distribution I'm working with. What are my degrees of freedom? Well, my degrees of freedom are 9, just n minus 1. Cool. Okay, so let me take a look at my degrees of freedom 9 over here. I'm actually going to screen cap this, I think, and try to move it over. Let me see if I can do this and make it look fairly nice. I'm going to move it over here so I can write on it. And I would also like to grab this index row at the top here. Okay. So I've cut out most of the table and put this in a format where I can kind of draw on it. So I'm looking just at my degrees of freedom 9 row with these important t indices, these t criticals on it. And I see that I have a t observed of 1.87. So for instance, my t observed is 1.87. If my t critical ended up being, say, 1.6, well, because 1.87 is bigger than 1.6, I could reject h naught. But on the other hand, if my t critical ended up being like 2.5, because 1.87 is less than or equal to 2.5, then I do not reject h naught. And I see that as I go from left to right here, these will be t criticals. These would be possible t criticals for different significance levels, different alphas. This would be for an alpha of 0.5%, an alpha of 1%, 2.5%, and so on. I see that my t criticals decrease. In fact, I can put 1.87, my t observed. I can look at it right between these two, 2.262 and 1.833. If my t critical that I grabbed off of this table was 1.833, because 1.87 is bigger than 1.833, because I'm more standard errors above the mean than 1.833, I can reject. So I can reject if t critical is 1.833 or 1.383. But I would not reject if I grabbed the t critical of 2.262 or 2.821 or 3.250. And to be clear, reject H naught, do not reject H naught. Or in other words, I cannot reject for alphas that are like 0.5% or 1% or 2.5%. Get a little more room here. But I can reject for alphas that are like 5 or 10%. Now remember back to our p-value discussion. Oh. How does this all tie into p-values? We can reject if and only if p is less than alpha. So in other words, I can reject for an alpha of 5%, but I cannot reject if alpha was 2.5%. This tells me that my p-value has to be between 2.5% and 5%. So my p-value is in the interval 0.025 to 0.05. I could come back up here and say, okay, what was my original question? At the 1% level of significance, can we make the claim? And my question is my p-value less than 1%? And the answer is no, it's at least 2.5%. So cannot reject H naught. We cannot make the claim, even though this 7.64 is kind of on the correct side of things. It's a little bigger than 7. It's not so much larger than 7 that I can be confident that it's not just due to sampling error. This could quite reasonably have been due to sampling error. And I just happened to get a couple of students who slept a little better last night. And so this could just be due to sampling error. I wouldn't want to reject the null in favor of the alternative and make the claim. If I did so, I would be making an error, a type 1 error between 2.5% and 5% of the time. And that's above the maximum allowable type 1 error rate of 1%. Now, as a side note, the more efficient way to answer this question as stated is just to use a rejection region method or a critical value method. But I wanted to show you this, how you can kind of back your way into estimating a p-value. Even if all we have is this t-table, right? We can't get the p-value, the probability of a type 1 error, to 4 decimal places of accuracy like we could, like we could on a normal table. We might have looked up and seen, you know, that the p-value was 0.0268 or something like that. To 4 decimal places of accuracy, we could get a lot of accuracy off of the normal table. For the t-table, really the best we can do is isolate the p-value between 2 of these probabilities. So in this case, it ended up being between 2.5% and 5%. But practically speaking, that's usually good enough, right? We're not typically going to be encountering a hypothesis test with a significance level of like 3.7%. Like we're not going to say alpha is 3.7%. That just doesn't happen in practice, really, right? If we had said alpha is 3.7%, I couldn't decide whether to reject or not based on the information I have here. But also under that same scenario, I wouldn't be able to decide whether to reject or not based on a rejection region or critical value method, because this table isn't granular enough for that. But I can estimate the p-value as between 2.5% and 5%. That's not less than 1%, the significance level. If I were to reject for this sample, I'd be making a type 1 error somewhere between 2.5% and 5% of the time, but I'm not allowed to make a type 1 error more than 1% of the time. So I do not reject H naught, and I can't make the claim. I can't be confident that this 7.64 that's a bit higher than 7 isn't just due to sampling error. Okay, any questions so far? Okay, and then moving on to our last test in chapter 8. So we're back to the Z world, and here we're looking at a Z test for a proportion. Now we know from confidence intervals that when we're dealing with proportions, we're kind of back in the Z world, right? We had a Z interval for a proportion. So we would guess that in hypothesis testing, we have a similar result, a Z test for a proportion, and we do. So let's consider a test for a population proportion that we have a null of P equals K, some population underlying probability of success. And the alternative is either P not equal to K, or maybe P less than K, or P bigger than K. Recall that our estimator, P hat, is approximately normal with mean of P and standard deviation of root PQ over N. That was just from our central limit theorem applied to P hat. So our test statistic, let me actually bump this down to the next line so it'll typeface it a little bit better, make it a little bit bigger, easier to see. So our test statistic is Z observed. Well, we're going to see a similar structure here. It's our P hat observed. So our sample value for P hat minus the null hypothesized value of P over the standard error. We have to be a little bit careful here. We might be tempted in the standard error to write square root of like P hat observed, Q hat observed over N. But note that when we compute this test statistic, it's under the assumption, assume H naught is true. And if H naught is true, then that tells me exactly what my standard error is. All right, so let's look at an example. Suppose we would like to test whether a coin is, quote, fair, that is, whether the probability of heads is 50%. And we want to conduct this test at the 5% level of significance, so alpha is 5%. We flip the coin 30 times, we get 21 heads. That seems to be a bit higher than we'd expect. We'd, kind of in a perfect world, expect to get 15 heads and 15 tails. 21 is a bit high, but I got a result that's a bit above 15, but is it so far above that it can't reasonably be due to sampling error and is indicating that the true probability of heads is not 50%? Or is it not so far away that I could just kind of write it off as, oh, well, that might just be due to sampling error? So the question is, at the 5% level, can we conclude the coin is unfair? Can we conclude that getting 21 heads on a fair coin where we'd expect 15 heads is so far away from the expected result that to dig in our heels and insist the coin is fair would be silly? Let's see. So just like before, we'll set up our hypotheses. We're now doing a hypothesis test regarding P, the population proportion, or the underlying probability of heads. And our question is the coin unfair? In other words, is it true that P is not equal to 50%? right? The coin will be unfair if heads came up too often or if heads didn't come up often enough. If P was like 10% or if P was like 90%, in both cases, we'd have an unfair coin. So this is a two-tail test. And the null hypothesis then P equals 50%. As always, before we start our computations, we do them under the assumption, assume H naught is true. And what does that mean? That means that P hat, the random variable, is normal with a mean of, if H naught is true, mean of P, or 0.5, and a standard deviation, the standard deviation of this distribution here, the distribution for P hat, I'm just going to call it sigma, is root. And again, we might be tempted to do something like P hat Q hat over N, but remember, assuming H naught is true, that means that P is 50%. So it's going to be square root of the null hypothesized value of P times 1 minus null hypothesized value of P all over N, or that's 0.5, 0.5 over 30. And if I jump over to my calculator, well, on the numerator, I have 0.5 squared under the square root. That's just a 0.5. And then that's divided by the square root of 30. So this gives me about 0.091. So this is my distribution of P hat. And maybe I'll take a p-value approach here. So I want to look at what is P hat observed. Where on this distribution does my P hat observed kind of index lie? Well, P hat observed is the experimental number of successes over number of tries, or that is 21 over 30. I can divide a factor of 3 from top and bottom. I get 7 out of 10, or 0.70. So P hat observed of 0.7 is somewhere to the right of 0.5. Now remember, the idea is that if I were to reject for this sample, this 21 heads on 30 flips, then I'd also reject anywhere further to the right, right? If I had gotten 22 heads on 30 flips, I'd also reject there as well if I'm rejecting for 21 on 30. Because 22 on 30 will be even further away from that 15 on 30 kind of perfect world scenario. So if I rejected for P hat observed of 70%, I'd also reject for anything further to the right. But this is the case where I reject a true null. I make an error there. That's my type 1 error rate. My p-value is the probability that I reject a true null, or in this case, that is, and let me leave a little room here, that is the probability that P hat, my random variable, is bigger than 0.70. There's a little detail I need to remember here, though, that this is a two-tail test. So if I were to reject for, say, 21 heads, where 15 would be the perfect world, in other words, if I were to reject because I got 6 heads too many, I'd also, of course, reject if I got 7 or 8 heads too many. But I'd also reject if I got 6 heads too few, if I got like 9 heads or 8 or 7 heads. So I have kind of a symmetric tail over here where I would also reject. If I were to reject for P hat observed of 0.7 or bigger, I also ought to reject for P hat observed of 0.3 or smaller. But practically speaking, that just means I double this probability. So in a two-tail test, I have to double the tail area in one tail to respect the fact that there are two sides where rejection could occur. Note that some folks will look at this and kind of philosophically or logically conclude that, well, since we did the experiment and got more heads than 15, like, why are we still accounting for the left tail? Right? Like, we did the experiment, and 21 heads is certainly not evidence that we would be we'd have a p well below 50%. But remember, two things here. Number one, we have to set up the structure before we run the experiment. We don't want the conclusion of the experiment to inform the structure when the structure is what we're using to analyze the results of the experiment. That's kind of a circular logic kind of deal. So we don't want to do that for that reason. And the other thing is that imagine that we applied the same test to 100 different coins. Maybe we're, manufacturing coins and maybe, doing it in a way that's not counterfeit. So, but we're manufacturing coins for people to flip because, I don't know, maybe that's the next big thing. And we want our coins to be perfectly 50-50. Well, some of our coins might come out as having too many heads, but some of them might come out as not having enough heads. We want to be able to catch both scenarios with our same test. So when we're dealing with frequentist statistics, we're kind of imagining that we can apply the same idea lots of different times in kind of independent scenarios. So we don't want to say, we don't want to just latch onto one tail of the two-tail test and do everything from there. We need to account for both tails. But sometimes people, kind of argue against that. So I wanted to give the argument in favor of, yes, this too actually needs to be there. It is important that it's there. Okay, so this is going to be, I'm running out of good colors to use. This is going to be, well, this is just a normal distribution question. I have some normal variable bigger than 0.70. Well, I just bring that back to a standard normal, z, bigger than, well, this is my index, 0.70 minus the mean, 0.5, over the standard deviation, 0.091. Or this is twice the probability z is bigger than, and this is 0.2 over 0.091. Or that's about, what would that be? 2.20. So my p-value ends up being twice the probability z is bigger than 2.20. Or maybe I'll use symmetry and write that as twice the probability z is less than negative 2.20. My right tail area to the right of positive 2.2 on z on the standard normal centered at 0 flips over to a left tail area to the left of negative 2.2. Okay, and what's the area to the left of negative 2.2? This looks like the right side of the table to use. And negative 2.2 with 0 hundredths, my area is 0.0139. Or what does this give me? 2.70%. So 1.39%, sorry, 2.78%. 2.78%. 1.39% doubles to 2.78%. So that is my p-value. If I reject for this sample, this 21 heads on 30 flips, if I reject fairness of the coin, then I'll make a type 1 error 2.78% of the time. A little under 3% of the time, I'll have flipped a fair coin, gotten a sample like this, and said this coin is unfair incorrectly. I'll make that error just around 3% of the time, but our maximum allowable error rate, the significance level, is 5%. So I can say, since the p-value, we see we have even more p's floating around now with proportion and all of that. So trying to be really careful to say p-value explicitly here, since the p-value is 2.78%. That's our kind of actual error rate if we reject. That's less than 5%, or alpha, the maximum allowable error rate. We're kind of within spec. We're not making errors too often if we reject. We reject H naught and conclude the coin is unfair. So again, what did I conclude? I concluded the coin was unfair. I didn't conclude that I'm really certain that P is actually 0.7. I guess in some sense technically didn't really even conclude that I'm quite certain that P is bigger than 50%. I really only concluded that I'm quite certain that P is not equal to 50%. And if I want to be really careful about how I say it, I really didn't even conclude that, did I? If I make a statement like I'm quite certain that P is not 50%, that really is saying that I think there's a high probability that the alternative hypothesis is true. That's really a Bayesian statement. Really what I did is I gave statistically significant evidence against H naught and in favor of H1, against fairness of the coin and in favor of the coin being unfair. So this is one of the things that if we get to our PowerPoint today, that we'll talk about is, how we actually report this result has a lot of different pitfalls, a lot of different, there are a lot of different ways that we could state the conclusion that kind of feels like it's about the same. It's like this statement or that statement or a third statement, they all mean the same thing, but they really mean different things. And we have to be very careful about that. And kind of the way that we would tend to be more likely to present the evidence, just the way that, our language works and the way that our thought process typically works, saying something like, on the basis of this, it's more likely that H1 is true than an H naught is true, something like that, is actually not a correct statement. Okay, so that wraps up chapter 8 on hypothesis testing. So I think at this point, I want to jump over to the PowerPoint slides, talk about interpretation analysis of hypothesis tests a little bit. And then if we have time, come back to chapter 9. I think I'm going to switch up the order just to make sure that we get that PowerPoint in. We're doing okay on time here. So give me 1 second to pause my screen share here and get things kind of set up. I'm going to pop the PowerPoint into chat. So if you want to follow along, you can. The PowerPoint is also available on the Blackboard site in the PowerPoints tab under supplemental material. So that's in chat. Let me get it open. I would have had it open to start with, but if you have it open, it won't let you post in a chat. So just one more second here and get my windows resized a bit, and then we will. All right, there we go. Jump back over. Okay, so I think everybody should be able to see the PowerPoint now. Yeah, it looks good. So again, PowerPoint, I popped it in the chat. It's also available on Blackboard. But we're going to work through this hypothesis testing and frequentist analysis, cautions and pitfalls. You can see there are 39 slides. We're not going to go through all of the slides in great detail. I'm going to kind of hit the high points as we go through here. So I've kind of split this into several different categories. The first being problems in a sense with alpha. So I mentioned before that when we run hypothesis tests, kind of typically we use alpha 5%, sometimes alpha 1 or 10%, but essentially never do you see somebody use like an alpha of 7% or 3.8%, or it seems kind of strange. Like, why this almost insistence on alpha equals 5%? Is there some like mathematical reason for it? It's kind of a gold standard. So why don't we use some other alpha? As far as I can tell, to my knowledge, this really originated in a book about 100 years ago from statistician Fisher. Um, and his book, and I don't mean to like, this isn't a slam against him or anything like that in any way. He did much of the groundwork for this frequentist analysis that we use today, and that's really been used over the last 100 years. But in his book, he says a deviation exceeding the standard deviation occurs about once in 3 trials, twice the standard deviation only about once in 22 trials, the value for which is p about 0.05 or 1 in 20, 1.96, standard errors is about 2. And he says it's convenient to take this point as a limit in judging whether a deviation is considered to be significant or not. So essentially, for the purposes of this book, deviations exceeding twice the standard deviation are regarded as significant. Basically, what he's saying is, if we think of the t numbers here, he's saying just pick t critical or z critical always to be 2. That's his argument here. And a critical number of 2 corresponds to a p-value around in the ballpark of 5%. So that's his argument. Now, keep in mind, 100 years ago, they didn't have calculators where you could just easily plug a bunch of numbers into and instantaneously get a number out. It was quite a lot of work to really do even, fairly basic calculations. So it's very nice to have kind of a couple of nice round numbers to work with when doing examples in a textbook. So that's where people leave it. But I think there's a couple of things. Number one, he's talking about what he's going to use in a textbook. I mean, he even says, whereas, it is convenient to take this point as a limit. He doesn't say like, this is a really good limit for these philosophical reasons. He just says it's convenient. We've got to pick a number for the purposes of our textbook. This is what we'll go with. But I think another issue is that he very clearly states, using this criterion, we should be led to follow up a negative result only once in 22 trials. In other words, we'll be misled, we'll reject the null in favor of the alternative and proceed forward with some point of scientific inquiry that actually ends up at a dead end because we shouldn't have rejected the null in the first place. And that'll only happen, say, once in 20-ish times. And even if the statistics are the only guide available, right? If you end up with rejecting the null in favor of the alternative and it's an absolutely silly thing, or if you look at the experiment and you say, oh, wait, well, there was clearly, a poor sampling method used here. Those are all kind of external factors that could be taken into account. Also from Fisher, he says the salutary habit of repeating important experiments, carrying out original observations and replicate, shows an appreciation of the fact that the object of our study is not an individual result, whether that's an individual person or even an individual study, but the population of the population of possibilities that we're studying. So I think that it's pretty clear that Fisher chose p equals 5% or 2 standard errors as basically kind of philosophically a preliminary indicator that's not an unreasonable one, maybe followed up with some more verification, and also as a convenient place to kind of set the mark for his book, where you say, okay, I'm going to go through some examples and we need to have a number that we're going to use as the cutoff. But I don't think that, there's some kind of 5% is set in stone, or that it certainly doesn't come from some like mathematical proof or theorem or something that says this is the best one to use. There's a medical literature rule of thumb that for alpha equals 5%, studies are typically powered to a power of 80%, or that means a type 2 error of 20%. We've talked almost not at all about type 2 errors, but we know that if we push alpha down, beta goes up and vice versa. So a power of 80% means that 80% of the time the null is truly false, the test will correctly reject it. So typically what a research protocol will look like is they'll say, okay, well, alpha is 5% because it's got to be 5% because that's what everybody uses. If I use alpha of 10% or something, the journal is going to say, go back and rerun the calculations with 5%. We're not going to publish it. And then they'll go to a statistician and say, how many participants do I need in my study to achieve a power of 80%? And that's essentially the cost of that study then is determined by how big it needs to be to get that power under an alpha of 5%. And that's not, that also requires some additional assumptions as well. Like, what do we think that the effect size is going to be, for instance? So let's consider kind of an example here. Suppose that a researcher tries 400 different random drugs to see if the drug causes the patient to recover faster. They want to test the mean time to recovery. The null is the means are the same. The alternative is the mean with the drug is less than the mean without the drug. And we're testing at the 5% level. What if the null is true for all 400 drugs? We just choose these drugs randomly. There is no reason that we would expect this drug to do a good job of treating this illness. So if none of the 400 drugs help, well, a 5% alpha means that there's a 5% false rejection rate. It means out of those 400 trials, we'd get 20 trials that look like, hey, this drug is a great success. It's really helpful for these patients, even though it actually isn't. So what's the probability that we get so kind of on average, we expect 20 false rejection. What's the probability we get at least one false rejection? It's essentially a guarantee. What if we took Fisher's advice and said, okay, when we get a significant result, let's follow it up with an independent follow-up piece of research. Have another lab use a different method and test the same drug for the same disease that we think works and see if they can replicate the results. As an aside, there's something called the replication crisis or the repeatability crisis in medical literature. And, maybe more often than we would hope is true, when researchers follow up important research, they can't replicate the results. So this group found that this treatment or this drug was clearly superior. Somebody tries to replicate that study and they get nothing. And 3 more labs try to replicate the study and they can't either. So, right, if we did the follow-up before we kind of take something as to be standard of care, take something as gospel, well, then it's kind of like, it's almost like there's a gate, right? And of 400, attackers or something trying to attack your city, only 5% of them make it through the gate. Well, 5% of 400 is still 20. There's still a lot of people that make it through the first gate. But if I had another gate behind that gate, then only 5% of the 20 who make it through the first gate are going to make it through the second gate. So we can get rid of, most of the remaining folks. We can get rid of 19 out of those 20 that won't be able to pass through the second gate, and only 1 out of 400 will be able to pass through both of the gates. So if we did 2 independent trials, we have an alpha more like 5% squared, or 1 out of 400. And on average, only 1 in 400 of those drugs we would think is actually useful when it's not, rather than say 20 out of 400 if we only relied on a single trial to change our standards or our points of view of the world. And now we see that the chance that we get at least 1 false rejection in 400 trials is about 2/3 or so. Not a certainty, still likely that we're going to get at least 1 false rejection, but probably not a whole bunch of them. So I think alpha equals 5% makes a good screen, but if we only see one piece of literature in the research that shows significance, we probably should think of that as a preliminary result, not an established fact. Okay, so the second really important thing to discuss here is the difference between statistical significance and practical relevance. So I have a little story here. I was listening to a podcast JAMA, the Journal of the American Medical Association, has a podcast series, and a lot of times if I have to travel somewhere in the car, I'll just pop that on, and they have several like kind of sub podcast series, and one of them is on statistical methods, and there are several of them. But so I was listening to one. I don't remember if it was a stats one or if it was just a general JAMA podcast. But the so the way that it works is kind of the host brings in a physician and kind of interviews them about some topic that they have some expertise in. And this physician was an oncologist, so they see patients and they treat patients with cancer. So they're, this physician's very much on the practical side of things, not on basic research, but they want to know, okay, what are the new things coming out that can actually help me to treat my patients better and make them better quicker or make them better more successfully. And something that he said is when the researcher was asking him, like, basically there's so much research that comes out every month, how do you keep up with it? And he says, well, yeah, you have to have a couple of criteria that you can use to just get rid of a bunch of the research right away. And he says, if I open a journal article and it looks interesting, I look at the sample size. And if I see a large sample size, I move on to the next paper. And the host was like, wait, if you see a large, do you mean a small sample size? Like, most people say, well, small sample size, not representative of the population. He says, no, large sample size. Why is that? Because the way that he looks at it is, well, the more relevant the result is going to be, if the researchers say, like, if we give people this drug, I think it's going to help them so much that it's going to be very obvious. I don't need a large sample to show that. Maybe a sample of size 50, a sample of size 100. That's as big as my study needs to be. On the other hand, if I think that there's a really small difference in the likely result between, say, the current standard of care treatment and our proposed treatment, if the researchers expect that difference to be very small, then to tease out that difference, they need a very, very large study. Now, these clinical trials and these studies are very expensive to run, so every participant that you put in, every additional participant costs a lot of money. So they're going to go to a statistician and say, how big does my trial need to be, given this effect size, to tease out, whether that's actually true or not, to reject the null if the null is actually false. And if the statistician comes back and says you need an enormous trial and you need to spend a lot of money, well, that difference in results is probably has probably such little practical relevance to the actual practicing oncologist, it's not going to change the way that they treat their patients. If one treatment is just very slightly better than the existing treatment that he's been prescribing for 10 years and has been successful, he's not going to jump ship to this other one because it looks like in one study it might be a tiny bit better. So that's an idea called the minimally clinically important difference, the MCID. And that's his argument, is he's saying, well, if you have a huge study that indicates to me that you don't think that your actual difference between the treatments is all that relevant. So it's not relevant to his practice. It's not likely to surpass the minimally clinically important difference that he's requiring. And he's not going to change his perspective on treating his patients on the basis of that. And that's what we kind of see in this example. Suppose we have some hypothesis test that the null is mu equals 100, alternative mu less than 100, and suppose the true mean is mu equals 99.9. If we were omniscient, if we knew all of the population data, we compute mu, we get 99.9, and we would know that the alternative is actually true, the null is actually false. We get a sample, we get X bar observed of 99.9, which we'd expect, on a sample of size 100,000. The p-value for the sample under the null is 1.75%. This is highly significant. That's well below 5%. But the question is this practically relevant, right? If we're talking about maybe, say, average IQ, well, IQ tests are normed to be 100. and maybe under some treatment or under some disease process, we're asking, is IQ impaired? Well, maybe IQ is impaired by 0.1 IQ points, but are we going to do anything about that? Are we going to provide any interventions to this person to remediate that 0.1 IQ point deficit? Well, no, that's essentially meaningless, right? It's not going to change their lifestyle or their career opportunities or anything like that, plus or minus 0.1 IQ points. So it's highly statistically significant, but it has essentially no practical relevance. And we needed a large sample size, size 100,000, for instance, to tease out this difference, to make this p-value small enough for it to be significant. And even more, if I bumped my n up to 1,000,000, if I use a sample size of 1,000,000, my p-value would be like 10 to the minus 11. People will look at these p-values that are really small like this, 10 to the minus 11, a tiny number. The chance that I make a type 1 error is extraordinarily small. Or kind of roughly speaking, I'm quite confident that the null is true and the alternative, or sorry, the null is false and the alternative is true. That's not quite right, but let's just go with it. But the thing is that if I had to use a sample size of 1,000,000 to get this small p-value, that's actually an indication that there's probably not much practical relevance, that the actual difference is probably so small that we don't actually care about it in any meaningful way. So just getting statistical significance isn't, it doesn't really tell me much about practical relevance. We'll kind of skip over this part, but this is just a discussion that pushing alpha down means beta goes up and pushing beta down means alpha goes up. And it's not always the best scenario to push alpha down and let beta go up. Sometimes sometimes type 1 errors are very costly and type 2 errors are less costly, so we push alpha down and let beta go up, and that's okay. But sometimes the opposite is true. Sometimes type 2 errors are very costly, and we might be happier to accept a higher value of alpha, knowing that's going to give us a lower value of beta. And sometimes both of them are kind of an equivalent cost, and we want to balance the two error rates. And I think the third and probably last big point that I want to make here is the misinterpretation of p-values. We get these p-values, maybe 1% or 3% or 0.5%, something like that. What does that mean? So we might want to make a statement like this. Well, the p-value, what is that? That's like the probability of getting this evidence, this sample that represents a certain amount of evidence against the null and in favor of the alternative. So the p-value is probability of seeing this type of evidence given that the null is true. And I might be tempted to say something like, because the p-value is small, then it's unlikely the null is true. Because the p-value is small, that means I have statistical significance. I can reject H0 in favor of H1, and therefore I think that it's unlikely that H0 is true. I think it's likely that H0 is false, so I can reject it. If we look at it in terms of these conditional probabilities, if I say it out loud like that, it seems like a perfectly reasonable thing to say. But if I look at it in terms of the conditional probabilities, I see actually what I've done is I've taken the p-value, that's the probability of evidence, conditioned on H not being true, and I've swapped the conditions. I've made a conclusion about the probability of what the conditions reverse, probability of H not being true given the existence of this evidence. But to make that swap, I really need Bayes' rule, and it's unclear whether that swap can reasonably be made or not. So for example, it's not correct to say that, say in a jury trial, since it's very unlikely for all this circumstantial evidence to exist, if the person on trial were truly innocent, then it's unlikely the person is truly innocent. That is not a correct statement. That's not a logically valid statement. It seems like it is. If you say this to 100 people, probably 99 of them would say, yeah, that seems quite reasonable. It's simply not correct. Sometimes this is called the prosecutor's fallacy because of this jury trial analogy. So let's take an example. Suppose there are two competing hypotheses. The person on the stand at the trial is either innocent of bank robbery or guilty of bank robbery. And again, let's presume that we have enough clarity in the law that we can, if we knew all of the facts and we were omniscient, we could tell without a doubt whether they fall into H0 or H1. And then suppose that there exists a plethora of circumstantial evidence. It's estimated that the probability of this evidence being true for a person who's innocent is 0.5%. So maybe the bank teller says the person was a male about this height, based on the little height thingamajigs they have at the doors to the banks. And they got in whatever, like a red Toyota Corolla, and drove away. And hey, this person on the stand is a male about that height, owns a red Toyota Corolla. We say, oh, the chance of all of that lining up, if the person were innocent, would be, say, only 0.5%. And we look at this and we might say, okay, this is highly significant. This is the p-value, right? This is the probability of this evidence occurring given the person is innocent is very small. The p-value is very small. We reject H0 even at the 1% level, even if alpha was 1%, where the bar is very high to generate a rejection, we'd still reject. So we, as frequentists, would declare the person guilty. But here's the issue. Let's think like Bayesians for a moment. What's the goal of a jury trial? It's to establish whether there is guilt beyond a reasonable doubt. So probably the way that we would take that is meaning that beyond a reasonable doubt means that something like it's more than 99% likely that the person is guilty. That, in other words, probability of guilty given evidence is bigger than 99%. Not probability evidence given innocent is less than 1%. So this isn't the same as generating rejection in the frequentist world. This is a Bayesian question. And these two answers aren't even concordant with one another. It's not like, well, these are slightly different based on a technicality, but they basically mean the same thing. That's not necessarily true. For instance, while we look and most people don't rob banks. So if we had no other evidence, we consider it pretty unlikely that the person on trial is a bank robber. So I looked at the FBI stats, and less than 1 in 10,000 people is, or sorry, less than 1 in 1,000 people is, or what? Yeah, less than 1 in 10,000. Yeah, I said it right the first time. Less than 1 in 10,000 people is guilty of robbing a bank. So if we picked a random person off the street, the probability they're guilty would be 0.01%, let's say, and the probability they're innocent would be 99.99%. If we take these to be our priors, what do things look like? Now, just a little aside, you might say, wait, well, this seems silly to take these as our priors. I mean, the person has been charged with a crime, they're on trial for it. Isn't it more likely, given the person's on trial, that they're guilty of the crime, more likely than just a random person pulled off the street? And I would argue we shouldn't think that way. And here's why. So if we look at the person on the stand, well, what's the job of the trial? The job of the trial is to present all of the evidence and to establish the facts of the case. So that's the job of the trial. But why did the person end up on the stand or on the defense, whatever, I keep saying on the stand, but really at the defense table? Why did they end up being the defendant in the trial? Well, first, the cop who was investigating the bank robbery identified this person and arrested them based on certain evidence. Maybe they matched the description, they got in a car that matched the description, etc. Well, then the DA had to decide whether to charge them. What information is the DA going to use when charging them? Well, probably the same information the cop used to arrest them, plus maybe a little bit more that came up in the investigation. Well, then the evidence has to be presented to the judge, and the judge has to decide whether there's enough to let it go to trial. But that's going to include the same evidence the cop and the DA used, and the same evidence the DA used to move forward with the charges. So we're kind of reusing the same evidence over and over again, and then presumably all of that same evidence is going to be presented again at trial. So I shouldn't take the person's, say, their height matching the height of the suspect. I shouldn't count that like 4 times, like once when the cop used it, and once when the DA used it, and once when the judge used it to let it go to trial, and then again when it's presented at trial. I probably should only count it once, right? So if the job of the trial was to present all evidence to establish the facts of the case, then I probably ought to look at this person who is at the defense table and initially presume, take as a prior probability that they are just a random person plucked off the street, and then see how all of the facts line up at the trial. Again, almost nobody does that, right? Psychologically, you see the person come in an orange jumpsuit and handcuffs or something. It's like we're already at like a 90% chance they're guilty, right? And it only takes, a little bit of evidence to tip the bucket in favor of that. Um, you know, Human beings are not very good at making rational decisions, especially in cases where we're put into situations where we don't make those types of decisions very often. I always say, like, I would be the worst jury to have in a jury. It would be almost impossible to convince me that the person is guilty. But that's beside the point. Okay, so let's look at the stats though. So if we take this as our priors, and I think I gave at least an argument as to why we should consider these our Bayesian priors. We should basically look at a random person chosen off the street. Probably they're guilty of bank robbery is quite small. And the question is, what is the probability they're innocent given the evidence presented against them? So probability of innocent given evidence, well, Bayes' rule equal to probability of evidence given innocent times probability of innocent over probability of evidence. There are 2 ways this evidence could have occurred. We could have gotten this evidence by chance and the person is innocent. That's the first term in the denominator. Or we could have gotten this evidence essentially as expected and the person is guilty. That's the second term in the denominator. So what is probability of evidence given innocent? That is actually our p-value. Probability of evidence given innocent is our p-value. So it's our p-value that is coming up in the first factor in the numerator down here. What's their prior probability of being innocent? 99.99%. That same term in the numerator is the first term in the denominator. And then if a person's guilty, we would expect all of the circumstantial evidence to line up in line with them. Now, there are things like witnesses get things wrong and stuff, but let's just suppose that if they're guilty, the evidence will line up with them, with their height or their description or the car that they own or whatever, 100% of the time. And their prior probability of being guilty is 0.001. So 1 in 10,000. If we do this calculation, note the probability they're innocent given this evidence is about 98%. So the probability they're guilty given this evidence is about 2%. And we were looking for a 99% cutoff to declare guilt. So the frequentist would have declared them guilty on the basis of probability of evidence given innocent being very small, the p-value being very small, less than 1%. But the Bayesian would say, but I think that there's only like a 2% chance this person is guilty. Well, we might ask ourselves then, well, how small does the p-value have to be for the Bayesian to agree? For the Bayesian to say, yes, it's 99% likely this person's guilty. And a little bit of algebra gives about 1 in a million, 10 to the minus 6. So the p-value would have to be like 10 to the minus 6 for the Bayesian to agree and say, yeah, I think the person is guilty too. I'm 99% certain that the person is guilty. Right. Often what we're looking at in a trial is more like frequentist-based information that's being presented. And the decision method that we're using is really a Bayesian decision method. And those two don't line up. So the decision we think we're making is a Bayesian decision, but what we're actually making is a frequentist decision, and there's not concordance between the two of them often. So here's a kind of a funny example. And as an aside, you can look up, there are lots of cases where bad statistics were presented at trial and people got convicted and later later exonerated when they realized that his statistics were bad. And it makes you wonder how many people were convicted and we haven't realized that the statistics are bad. Nobody looked into it enough. There's a lady, Lucia de Burke, who's a famous example. So here's a somewhat of a joke in this vein. So it asks, did the sun just explode? It's night, so we're not sure. Person on the left says the neutrino detector measures whether the sun has gone nova. If it rolls, then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. So they say, let's try detector has the sun gone nova. It rolls the dice, and then it says yes. And the frequentist statistician says the probability of the result happening by chance is 1 in 36. So the probability of the sun did not explode, but it rolled 2 dice. They both came up 6. That's 1 in 36. That's about 3-ish%. Since p is less than 0.05, I conclude the sun has exploded. And the Bayesian statistician says, bet you $50 it hasn't, right? It's essentially the same as the way that a lot of our jury trials are conducted. We can see the silliness here. We can see that this is clearly, this piece of evidence is clearly silly in this case, and doesn't really correspond to the thing that we're trying to show. But we don't always see that so clearly. Okay, so really quick note on publication bias. If I told you that I gave my medication to a bunch of test subjects who were very ill and 50 of them recovered much more quickly than expected, would you think this represents strong evidence for the efficacy of my drug? And I think that most people would say, well, how many people did you give your drug to, right? If you gave it to 50 people and all of them recovered very quickly, probably yes. If you gave it to 5,000 people and 50 recovered pretty quickly, 1% of them, maybe that just happened by chance. So, so the number of positive results, the number of successes only tells half the story, or maybe even less than half the story. We need to know the number of negatives as well. But let's zoom out. If I had one trial, it's easy to see that we're missing that piece of information. But if I go into PubMed and I search for a specific treatment or disease or something, and I find, three published papers that all say, hey, we did this experiment, we found this successful result, it's published, it looks like this works. Well, a lot of people would just take that and run with it and say, oh, that's established science. And never think to ask the question, okay, that was 3 positive trials, 3 positive results. How many other trials were there? How many trials are there that tried this treatment for this disease and came up with nothing? Came up with just, it didn't make any difference. If there were maybe 4 trials total and 3 of them were successes and one of them was, not really sure, doesn't seem to make a difference, that might be pretty good evidence. If there were 3 trials that came up with successes and, 15 trials that came up with nothing else, well, that's less good evidence. So when we're looking at papers or doing research, we always ought to have in the back of our mind, okay, like the things that are being published are more likely to be the positive results where the researcher found what they were looking for and got some kind of interesting result. But there might have been a lot of other researchers who tried similar research, who tried to get a similar result and just went nowhere. So these papers that we're looking at when we do a literature search are kind of like the people who got better really quickly. But in the back of our mind should be, okay, well, but these are certain published papers, certain pieces of research out of a body of research. What does the rest of that body look like? And it's often unclear. Also, on the back end, if we have a few, good papers that have established a result, somebody coming out and in their lab taking the time to verify that, to try to run similar research using an orthogonal method, that's not likely to get you on the cover of Nature, right? So it's much less prestigious to do that. So people aren't incentivized to do that. So something that has come out a little bit in the last maybe 5 or 10 years is some journals, but not the big ones as far as I know, have seen this problem and they've basically said, well, if you want us to publish the result at the end of your research, you have to register your research protocol with us at the beginning of it before you get any data. So that way they kind of have an idea of what's the total number of people who are investigating this idea or working in this area, and then how many of those got a positive result. But as far as I know, not many journals do this, and not the bigger ones. So, this would be one way to tackle it, or even just to have a general database where, if you want to publish in any of these journals, you have to have registered your study in that database before you started it. But I don't think that there's been much movement on that. And then the last kind of challenge of hypothesis test is it's just kind of an awkward setup. We have something that we want to show is true typically. Typically, we want to show H1 is true. So we kind of assume the opposite of what we want to show is true. We give it the benefit of the doubt even. We gather data, we kind of ask, how strange would it be for the opposite of what I want to be true? How strange would it be to insist that that's true? If it would be quite strange to insist that the null is true, and less strange to go with the alternative, then I flip and I go with the alternative. So it's an argument by contradiction. The logic is valid, but it's not easy to explain and it's not easy to interpret. So at the end of all of this complaining, why are they used? Well, number one, there aren't a ton of options available. Number two, Bayesian analysis is somewhat subjective because you can set your prior, right? Maybe you disagree with me in the jury trial example, or should we use the crime rate for the area that the bank was located in, or for that city, or for that state, or for across the whole US, or, where should we pull that prior from? Even if we agree on the type of prior that should be used, what data set should we use to establish it? Or on the more malevolent side, if I'm a researcher and I want a certain outcome, in particular, if my job is dependent on getting a certain outcome, right, or my grant money or whatever, will I choose priors intentionally to make it more likely that my result looks like it's, quote, significant or the equivalent in the Bayesian world? Right. It's easier and kind of levels the playing field to just say alpha's 5% period, end of story, that's your bar. But when we have priors floating around, well, on one hand, priors can be good because they take into account the strength of the evidence, that we've experienced before. Like, has the sun exploded? Probably not. But on the other hand, they can be subjective. And also, frankly, well-performed and well-analyzed hypothesis tests generate solid results. And I made this graph. It's a little complicated to explain, and we're running out of time. But basically, what this is on the horizontal axis, this is the prior probability of the null being false under the Bayesian paradigm. On the vertical axis, we have the posterior probability from the Bayesian perspective of the null being false. And this is under a rejection at the 5% level. So basically what we're saying is if we move from left to right, this is the Bayesian person in their prior being more and more and more certain that the null is actually false. So something like in the middle here would be about 50-50, where the Bayesian statistician is saying it's about a coin toss between the null being true or false. Then given that the frequentist looks at the result of the experiment and rejects the null, what's the probability the Bayesian would also say that the null is false? It's right up here at about 95%. So if we have about a coin flip, if we have where it's about equally likely between the null and the alternative being the right answer, then if the frequentist rejects at the 5% level, the Bayesian will say there's less than a 5% chance of the null being true. So that statement that is, technically incorrect and can sometimes really badly mislead us, like in that jury trial example. Well, if we have a null and alternative that are about on equal footing, the Bayesian and the and the frequentist will essentially completely agree. Where we have a problem is whenever the probability H not being false is quite low, right? When very few people are bank robbers, for instance. Then, given that the frequentist rejects the null, if the Bayesian says that the probability H not is false is very low, under the same type of scenario where the frequentist would reject the null, the Bayesian isn't really very much convinced at all. They might think that there's a 5 or 10% chance that the null is false now, where the frequentist has abandoned the null altogether in favor of the alternative. The Bayesian would say 5 or 10% chance the null is false. In other words, 95% chance that the null is true still. So it's really whenever we have a very low likelihood or a very low prior for the null being false that the Bayesian and the frequentist really disagree a lot. But when the balance between the null and the alternative, that prior distribution is more balanced when there's balance between the two. And the Bayesians and the frequentists kind of agree. Don't tell them I said that. They might not be happy with agreeing on anything, but that is the case. Okay, so any questions on any of that? Okay, I think we'll end a couple minutes early, and next time we'll kind of wrap up the last little bit in chapter 9, talk a little bit about chapter 10, correlation and regression, and yeah, that'll wrap up our discussion for the course. Like I said, if you want to take the final a little early, say if you want to take it this weekend, you can go back to the fall 2024 lectures and look at the last couple lectures. You can pull up the correlation or regression lecture and get that out of the way before you take the exam. Otherwise, I will see you on Monday. Have a good one.